I'm Jimena Ferraris. I'm a researcher at Broberger Lab at Stockholm University at the Department of Biophysics and Biochemistry. So I'm a veterinarian by training, and as soon as I started studying, I started to work in vet clinics, but also very early in a lab doing research, actually in a topic very related to what I do now. And after completing my studies, I worked for a pharma company for a couple of years, but then I was missing the lab, so I came back to the lab for a PhD, and I did my PhD in Argentina, where I'm from, but also in France, where we had a collaboration, so I was going back and forth, and between the two countries, I completed my PhD. And then after looking for positions abroad, I decided to stay in Argentina more for personal reasons. And I had a postdoc position there at the University of Buenos Aires, and then I had a assistant professor position. But some years into that, I realized I wanted something else, so I decided to move abroad. And I actually wanted to move to another country. I was looking for labs in Canada, but you know how life is, and I got surprised by meeting my current supervisor, Christian, in a meeting in the States, and he had an open position. And I joined the lab with a fellowship first, and then that turned into a permanent position here at Stockholm University. When I came, it was first at Karolinska Institute, but then we moved to Stockholm University, and since then I've been working with him. We work with a group of neurons that are in the hypothalamus that are dopaminergic and control prolactin secretion. And prolactin is a hormone that is released by the pituitary and is very important in many reproductive processes. And of course, lactation is a hormone that will allow the mammary gland to produce milk. Now, as we know, this milk production doesn't happen all the time. It happens only after birth. So one of the things we study is how these neurons change, how they control lactation at a specific moment, how these neurons are shaped during pregnancy to promote then lactation. But mostly we study which factors that are not exactly in the brain, that are hormones, control how these neurons behave. These neurons have a very particular organization in the rat brain, and these are coupled by gap junctions, so they oscillate, so they have this very particular way of firing, and they do that in a coordinated manner. And this is plastic. This will adapt in different physiological conditions. So also, apart from the endocrine control of these neurons, what we study is how this network is built and which components make them plastic, and how can they adapt to different physiological demands for this hormone that is important during lactation, but also during the reproductive cycle. So in the lab, we use from in vivo techniques to very molecular approaches. Myself, I use mainly electrophysiology in brain slices, in acute brain slices, ex vivo, of course, calcium imaging, as well, a lot of microscopy, light microscopy and electron microscopy. And what we do is always try to combine techniques. So the same question is answered by different approaches. So, for example, if we want to know what is happening to a neuron in a certain to these neurons in a certain physiological condition, what we will do is to do electrophysiology to it, then fix and post-process it, even for light microscopy or electron microscopy, try to understand how not only these neurons works in an isolated manner, but what it happens when the physiological condition changes, for example, when hormonal level changes or along the estrous cycle, and how this impacts in, for example, animal behavior. I don't do the behavior myself, but I do this mostly all these ex vivo and in vitro techniques. I think the most exciting is this that I mentioned at the beginning, that is that this system is not static. You might think about a gap junction connecting network as something that's stable and will be unchanged, but it's actually very plastic. And we found how hormones control and inhibit these neurons, how that times the moment of the hormonal release, which will then be will control this in a more systemic way. So you have a hormone coming from the ovary controlling the brain controlling the pituitary, this hormone then controlling other reproductive functions, and like that this circuit, and that this is done in a very specific manner, that estrogens can have different ways of modifying neuronal activity. It's described in other parts of the brain and in other hypothalamic neurons, but we found a very specific way in which estrogens, for example, control these neurons, and how this system can be plastic, I think, are the two main findings with the brain slices approach. So about slicing, we use 250 micrometers slices to 300 micrometers, depending on the which cells we're aiming for, but most of the time 250 micrometers. With exact parameters, we use 1.25 millimeters amplitude and 80 hertz for our hypothalamic brain slices, but that will change if we are slicing for cortex and other projects. What I think is the most important when you start slicing is to be patient. This takes, I mean, it might sound obvious, but it takes time for learning. Not the machines are very simple to use, but what you need is to know how your tissue is, how to handle the tissue, how to make perfect solutions, and that takes time. So the first thing I would say is that you need to be patient, and you need to continue to be patient. You don't want to hurry up things. You need to be fast, but you need to be precise. So the first thing to have good slices is when you take your tissue. Taking out the brain without damaging it takes some training as well. So you want to do it, again, to be fast, to put it immediately into the cold solution. We use sucrose-based solutions for slicing. There are others that can be used, but those are the ones that work best for us. The solution needs to be fresh, and you want to check up everything in that solution. You want to check the osmolarity, you want to check the pH. This again sounds obvious, but as people do this every day, they tend to stop doing that. But you want to make sure that your solutions are perfect before starting, that are really cold. We used smashed ice solutions. Then you want to get into the vibratome as soon as possible, place the brain in a way that is already ready for getting the slices you want, so you don't have to further manipulate the brain, and start your slicing. You want to use a very sharp blade. We use ceramic blades that were a game changer for us. We were not using it before, and that really changed the quality of our slices. You want that blade to be really clean, and you want to keep it clean so it lasts as much as possible. So you need to be very careful when handling it and when cleaning it afterwards. And again, while slicing, you want to be patient. You want to slice at a low speed. In the vibratome we use is 0.1, the speed we use, and let the blade go through the slice and let it finish, and then once it's finished, stop and collect your slice very carefully and transfer it to the chamber. So I would say patience, good solutions, and good handling of your tissue and your vibratome are the key factors. So where I see the field going is to including more of the brain-body interactions. So of course, hormones have been studied for many years, and we know that they influence how the brain works. But now this is taking more into considerations how hormone controls neuronal circuits, their properties, even the electrophysiology, from the circuits to the molecular level. And this is very important to consider. The brain is not something that controls everything and it's there because it's the most important part of the body. That might sound funny, but it's how many neuroscientists see it. And it's actually in a body that communicates with it and controls it. And hormones are a crucial way of this communication to happen. And the second side to this is that more female research is being included. So we are basing our conclusions mostly on data taken from male animal models. And the scenarios can be very, very different in a female reproductive context or in a female endocrine context, from a female perspective. So more research is needed, because some diseases or conditions are very different in males and females, but also there are conditions that are unique to females. For instance, menopause, lactation, pregnancy, that people would be surprised, but it's really, really understudied. And I see how the field now is turning into, oh, this was different in females. We have included females in our cohorts. And specifically to what I do, now more and more papers are being published trying to explain how hormones control neurons, and this body-brain communication is becoming more and more important.